Hi everyone, this is Professor Majumdar and you are watching EUDA Plus, the professional CAD/CAM solution provider. Let's get started. Hello viewers, today I'm going to show finite element analysis of an overhanging beam under a combination of concentrated load and also uniformly distributed load. Let us see the statement of the problem. Using ANSYS mechanical APDL, draw the shear force and bending moment diagram of the beam as shown in figure and compare the results. So this is the problem. A beam of total span 15 meter and it is supported with uniformly distributed load at the left hand side and right hand side. Left hand side we are having a uniformly distributed load of 1000 Newton per meter and right hand side it is 1600 Newton per meter, and at point C and D we are having a concentrated point load of 8000 Newton and 4000 Newton. It is an overhanging beam and we are providing a support at A and B. We need to analyze this one using ANSYS mechanical APDL and then we have to compare these results with the question paper itself, because in the question paper itself we are having the results that we compared with the results obtained from ANSYS mechanical APDL, right? So without wasting time, let us start our analysis using ANSYS mechanical APDL. Okay, right. First of all, we need to create a directory and in that directory we need to save everything. Okay. Next to that, we need to change the title of this one. That can be done from file, change title, and we are keeping the name of this one as FEA10. Okay, to see the title we can click on plot replot, so it is visible at the lower left corner. Now we need to define what type of analysis it is and it will come from preferences. So preferences is a structural analysis. Okay, now we need to define elemental properties. It will come from preprocessor. Element type, add, edit, delete. So we need to add it. We're considering beam with 35 strain and element type reference number is 1. And from options, you can select element behavior as cubic form. Okay, done. Let us close it. Now we need to provide material properties. So material models, structural, linear, elastic, isotropic, and we know that it is having modulus of elasticity of 2 into 10 to the 11 Newton per meter square and Poisson's ratio is 0.3. So modulus of elasticity is 2e11 and Poisson's ratio 0.3. Okay, done. Now we need to provide sections and it is having a square cross section of breadth equal to 0.01 meter and height equal also 0.01 meter, right? So breadth equal to 0.01 meter and height also 0.01 meter. Okay, done. Now we need to start modeling. Create key points in active coordinate system. We know that total span of the beam is actually 15 meter and first key point will be created at origin. So apply. Second key point will be at a distance of 5 meter from origin. So 5 along X. Apply. Third one will be at a distance of 7.5 meter from origin. Apply. Fourth one will be at a distance of 12.5 meter from origin. Apply. Fifth one will be at a distance of 15 meter from origin. Apply. Now one extra key point should be provided for the orientation of the beam, and let us provide that one at a distance of x equal to 0 and y equal to -8. Okay, we created all the necessary key points. Now we need to join all these key points in the form of lines. So create lines, straight lines, and let us join key point number 1 and 2. Done. Now 2 and 3. Done. 3 and 4, and finally 4 and 5. Okay, we joined all the lines excluding that extra key point 6 which is required for orientation of the beam, right? Now we need to mesh it. Meshing, and first of all we need to select mesh attributes. We need to consider that orientation key point also, so we are selecting all the lines, and orientation key point also we are considering. Okay, we are selecting orientation key point 6. Okay, done. Now we can mesh it. So size controls, manual size, lines, all lines, and we are considering number of elemental divisions for each line equal to 10. Okay, done. Now finally we can mesh it. So mesh lines, pick all, meshing is complete. Now we can apply our boundary conditions and that will come from loads. Loads analysis type, it is a new analysis and it is static structural analysis. Okay, done. Now we need to define loads. Apply structural displacement on key points. It is an overhanging beam and it will be having support at two different locations. Let us see the lines. So plot lines. We need to provide a support at this location and also at this location, right? So select key point number 1, apply. Let us select ux, uy and uz, and also rotation x and also rotation y. So the key point is restricted to move along all these points. Apply. Let us select the next required key point at this location. Okay, here in this case it will be restricted to move along uy, uz and rotation x and rotation y. Okay, done. Now we need to apply 2 point loads at this location and this location, right? Let us see that question paper itself. We need to apply point load of 8000 Newton at location C and 4000 Newton at D, right? So structural force moment on key points. Let us select this key point, apply. It will be in the y direction, Fy, and it will be in the negative, so it will be minus 8000 Newton. Apply, and second one it will be minus 4000 Newton again. Okay, we have applied our concentrated load. Now we need to apply uniformly distributed load at this location and also at this location, right? You can see here uniformly distributed load of 1000 Newton per meter, and also here it is 1600 Newton per meter. Two different types of uniformly distributed load to be applied, right? So it will be pressure on beams. Let us select from box notation. We are selecting these specific key points or nodes. We have selected all the specific nodes, apply, and it will be 1000 Newton per meter in the downward directions, right? So it will be minus 1000 at starting node, and also at finishing node also same, minus 1000 Newton per meter. Apply. First uniformly distributed load is applied. Now the second one to be applied at the extreme right hand side, and that value is actually 1600 Newton per meter, right? So let us select by box, selected. Okay, this value is starting from minus 1600 Newton per meter at starting node and finishing at with the same number, minus 1600 Newton meter. Okay, done. So we have applied both the concentrated load and also uniformly distributed load at specific locations. Now we need to solve it. So solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done, so everything is perfect. You can see our results from general post processing. Okay, let us close it. General post processing. First of all, we need to read results from last set. Read results last set. Now we need to define elemental table. So define table, and for shear force and bending moment diagram we need to select some specific numbers. For bending moment we need to select SMIS 2 and 15, and for shear force we need to select SMIS 5 and 18, right? Let us add it, and from drop down menu we can select by sequence number, and SMISC it will be 2. Apply, and again repeat the process. It is by sequence number and SMISC 15. These two numbers will be for bending moment diagram. Okay, apply. Next one for shear force, selecting by sequence number and SMISC it will be 5. Apply. And the last one again by sequence number and it will be SMISC 18. Okay, we have selected all the numbers. First two numbers SMISC 2 and 15 for bending moment, and next set 5 and 18 for shear force. Okay, let us close it. Now first of all, let's see the results from listing. So list results, and we have to see reaction solution. Let us select all items, right? You can see that maximum reaction is occurring at node number 1 and node number 42. Node number 1 along y direction it is 10,000 Newton or 10 kilonewton, and also at node number 42 is 11,000 Newton or 11 kilonewton, right? Let us check this one from actual question paper also. It is 10 kilonewton and 11 kilonewton, right? Let us see it from a question paper for comparison. You can see exactly same. At node number 1 it is 10,000 Newton or 10 kilonewton, and at extreme right hand side it is 11,000 Newton or 11 kilonewton. So it is exactly same, right? Done. Next to that we need to see our results, both shear force and bending moment from listing results. So element table data, and you can select all the numbers SMIS 2 and 15 for bending moment and SMIS 5 and 18 for shear force. So this will show all the shear force and bending moment at a specific nodes, right? Okay, let's see it. So this is the data. It is representing shear force and bending moments at all locations, right? You can see it in a better way. So we are having total 40 nodes, and at each specific node it is showing shear force and bending moment. First two columns represented by SMIS 2 and SMIS 15 representing bending moment, and third and fourth column represented by SMS 5 and 18, it is representing shear force, right? Each specific node is providing data at specific locations representing bending moment and shear force. We can see at the last moment, maximum bending moment is occurring at node number 11. It is 37.5 kilonewton meter. It is occurring at node number 11 and 10. And minimum bending moment is occurring at node number 30 and 31. It is minus 5000 Newton meter, right? Similarly, you can see here maximum shear force is occurring at node number 1. It is 10,000 Newton, and minimum shear force is occurring at node number 21. It is 7,000 Newton. Now we can see all these results from plot also. Let us see plot results. So plot results. Can to plot line elemental response, and we want to see all these results. First of all, let us see bending moment diagram. So it will be SMS 2 and SMS 15. Okay, let us see the drawing. So it is showing maximum shear force is occurring at this location. It is 37.5 kilonewton meter at this location, and minimum shear force is occurring at this location. It is minus 5000 kilonewton meter, right? Now we'll see the results from our question paper also and compare these results, right? Let us see this from question paper. It is showing maximum bending moment is occurring at this location. It is 37.5 kilonewton meter, and minimum is occurring at this location. It is 5 kilonewton meter, right? It is exactly same, so it is validating our results. You can see it, 37.5 kilonewton meter at location C and 5 kilonewton meter at location B. So it is exactly same. Okay, right. Now we'll see the shear force also. So we can change the numbers, SMS 5 and SMS 18. That will represent shear force. Okay, let's see. So it is showing that maximum shear force is occurring at this location. It is 10,000 Newton or 10 kilonewton, and minimum is occurring at this location. It is minus 7,000 Newton or minus 7 kilonewton. You can see our results from our question paper also. Let us compare this one. It is showing exactly same. Maximum is occurring at key point 1. It is 10,000 Newton or 10 kilonewton, and minimum is occurring at this location. It is minus 7,000 Newton, right? So it is exactly same. It is validating our results. What we got from ANSYS mechanical APDL is exactly same compared to our theoretical results, right? Now we can see the animation of this beam. So what we'll do is can plot the elements, and also we want to see that beam in the form of 3D. So plot controls, style, size and shape, and display of elements should be on. Okay, right? Now for better view, we can see the isometric view or oblique one, anyone. Let us see the oblique one. You can see this is the beam with specific cross section of 0.01 meter by 0.01 meter, right? Now you can see the animation of this one. So plot controls, animate, and we'll see deform results. Translation along y direction. So UI with the default setup, you can see the translation along y direction. Okay, now for better view, we can decrease the delay period. Let us see how the beam will be vibrating, right? So this is the animation of this beam. Okay, excluding this one, you can see deflection, or you can say displacement along y direction also, that can be viewed both from plotting and listing. Let us see plotting things of displacement along y direction, right? So list results, nodal solution, DF solution 1, y component of displacement. This is showing displacement of all these defined nodes. You can see maximum displacement is occurring at node number 26, and it is 3136.8 meter. It is very high, right? I want to see the plot results of these things. The plot results can to plot nodal solution, and want to see deformation along y direction. So displacement along y component. You can see here maximum displacement is occurring here. So it is minus 3136.76, right? A defined node, it is having different deformation or different displacement, right? So let us close this one. So this is all about our today's video. This was a very simple finite element analysis of an overhanging beam with a combination of uniformly distributed load and also concentrated load. In this analysis, we found shear force and bending moment diagram of that beam, and we compared that results with the theoretical answer, and it is exactly same compared with the theoretical answer. Okay, so thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.